this session, we will introduce several basic speech recognition systems, especially HMM-based speech recognition. The basic models of a speech recognizer include feature extraction, which represents a speech waveform into feature parameters, training, which generates templates for each mode, pattern classifier, which analyzes the pattern of the input data based on the pre-trained templates. The recognized result will be output with a kind of decision logic. Sometimes the knowledge sources are also used to help pattern recognizing process. MFCC coefficients are commonly used as features in speech recognition systems. The subspectrum coefficient obtained on the male spectrum is called the male frequency subspectrum coefficient. MFCC coefficients are commonly derived as follows. First, take the Fourier transform of a windowed expert of a signal. Second, map the powers of the spectrum obtained above onto the male scale using triangular overlapping windows. Third, take the logs of the powers at each of the male frequencies. Fourth, take the discrete cosine transform, DCT, of the list of male log powers as if it was a signal. 5. The MFCCs are the amplitudes of the resulting spectrum. Then the MFCC coefficients need to be normalized and to add dynamic features with temporal derivatives. The standard MFCC feature only reflects the static characteristics of speech parameters, and the dynamic characteristics of speech can be described by the difference spectrum of these static characteristics. Sometimes, the feature vector in speech recognition add dynamics MFCC features, such as delta and delta delta, first and the second order frame-to-frame difference coefficients. Combining dynamic information and static information as a feature vector can greatly improve the performance of the recognition system. For an input frame with 20 milliseconds at 8 kHz sampling rate, the extracted MFCC feature vector contains totally 39-dimensional parameters, including 13-dimensional standard MFCC coefficients, 13 first-order difference coefficients, and 13 second-order difference coefficients. Let's start with simple task, recognize yes or no. Firstly, the speech utterance will be transformed into 39-dimension MFCC vectors, frame by frame. Then, we use vector clustering for training. The 39-dimensional vector space is clusterized into different subspaces by means of k-means and Euclidean distance measure. The 10 utterances yes in the training data lead to several typical vectors or code vectors by VQ clustering to form the codebook yes. Similarly, the 10 utterances no generate another codebook no. If the training data is large enough, the number of typical vectors could be large. which means the size of codebook could be large. The pre-trained codebook will be used as a template in yes and no recognition through vector quantization. When testing, the recognizer outputs the corresponding code label by searching the smaller quantization arrow and then uses statistical analysis to get the average results. Just now, we used VQ to build up a simple speech recognition system. There is another way to make a statistical speech recognition system using hidden Markov model HMM. HMM can be used in speech recognition because a speech signal can be viewed as a piecewise stationary signal or a short-time stationary signal. In a short-time scale, for example, 20 milliseconds, speech can be approximated as a stationary process. Speech can be thought of as a Markov model for many stochastic purposes. For the simple task, recognizing yes or no, we will train two HMM models for yes or no separately. When testing, we will use the HMM models to describe the unknown speech and decide which output has the maximum likelihood. Under the given HMM model, yes, there is a probability Pxw1. As to another HMM model, no, there is another probability Pxw2. Compare these two probabilities, then choose the larger one as the output. Finally, we make a statistical analysis to get the average results. Here, we use Baum-Welch algorithm to train HMM model and use VDB algorithm to do the pattern classifier. The decision logic in HMM-based recognition is to choose the larger conditional probability, not the smaller distance or quantity error in VQ-based probability. Considering an original way, when we have some concept in our brain with a sequence of symbols or words, we will pronounce the speech waveform according to the concept. Then we record the speech in our mind and parameterize it into a series of speech vectors. For the recognizer, we need to combine the speech vectors and convert them into the original words. The difficult task is how to convert the speech vectors into different symbols or words. We could use HMM model to finish the recognition task. In HMM-based speech recognition, it is assumed that the sequence of observed speech vectors corresponding to each word is generated by a Markov model. Speech recognition often uses the left-right HMM model, which is a finite state machine and also a doubly stochastic process involving at least two levels of uncertainty: a random process associated with each hidden state, and a Markov chain, which characterize the probabilities relationship among the states in terms of how likely one state is to follow another. The target of speech recognition task is to find the most possible states by computing the maximum likelihood under the given model lambda and the observation sequence O. In HMM-based recognition system, there are mainly two problems, including HMM training and recognition by HMM. Before the recognition task, HMM model should be trained with a set of speech database. The training process uses a Baum-Welch re-estimation algorithm. For example, in isolated word IW recognition system, such as command and control with English numbers, HMM training is used to estimate several models as the reference templates for each number. In the recognition procedure, likelihood computation is carried out based on the pre-trained HMM models. The maximum conditional probability is selected to output the recognized word. The recognition procedure using HMM can be realized by VDB decoding. The extension from an isolated word to continuous speech simply involves connecting HMM together in sequence. Each model in the sequence corresponds directly to the assumed underlying symbol. This could be the whole words or so-called connected speech recognition, or subwords such as phonemes for continuous speech recognition. The search network for continuous speech recognition could have several levels. A word is composed of several phonemes. Each HMM corresponds to a word or phoneme. Each phoneme in a word corresponds to a number of modal states, typically 3 states per phoneme. When saying a word, the speaker stays in each state for one or more frames and then goes on to the next state. Thus, continuous speech recognition by HMM can be realized with state level, HMM level, and word level. That's all for this session. See you next session.